Hey everyone, Connor Mead with the Calculation Center here again with another video on our calculus series. This time we'll be talking about the rules of integration, by which I mean I want to talk about how we can kind of combine results we got for simple functions into more complicated results using kind of properties we know of the integral. I've written out some of them here. There's more complicated ones down below that we'll go over it briefly, but they really do warrant their own video, so we won't be going into too much depth on them right now. So here are the kind of most basic examples of these rules. So this first one here, it says that the integral of c of f of x dx is equal to the integral of c times f of x, the integral of f of x dx, okay? So this is for a constant number c. We can move it out in front of the integral to simplify our problem. So for example, if the c was equal to 5, this would be equal to the integral of 5 f of x dx is equal to 5 times the integral of f of x dx. Similarly, this is also a rule we had for differentiation, that the integral of f of x plus g of x dx is equal to the integral from f of x dx plus the integral of g of x dx. Now, these two properties in combination are called linearity, and they generally make things very nice to work with. And I should also point out that this, although I've written these out for definite integrals, these two hold for, or rather, I've written this out for indefinite integrals. These two results hold for definite integrals as well. These next two, however, are specific to definite integrals and not indefinite integrals, because they're to do with the bounds of integration. So the third one here, it says the integral from a to b of f of x dx is equal to minus the integral from b to a of f of x dx, okay? So this just means that we can swap our numbers here by putting in a minus sign outside. So that what that means is the integral from 0 to 1 is equal to minus the integral from 1 to 0 of some function f. Okay? So this one doesn't come up very often, but if you ever need it, you can use it. And lastly on this list, we've got this kind of rule about splitting up the integral. Okay, so we're not talking about a sum here on the left-hand side. We're talking about the integral from a to b of f of x dx. This is actually equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Okay, in general, we interpret this c as being in between a and b, but it's technically true even if it's not. So roughly speaking, this means if we've got a function here going from a to b and we want the integral, the area under this graph, this is the same as if we have a point in the middle c and just add up this bit and this bit, the integral from a to c plus the integral from c to b. Okay? So I've got some examples that we can use use these rules to solve, given that we already know some simple integrals. So for example, down here, I've just written this out already, the integral of 3x squared minus 2x plus 4 sine of x is actually equal to the integral 3 times the integral of x squared dx minus 2 times the integral of x dx plus 4 times the integral of sine x dx. So this is equal to x cubed over 3 times 3 is x cubed, minus 2 times x squared over 2 is x squared, plus 4 times the integral of sine x, the integral of sine x. So we just need to be a little careful here. What do we need to differentiate to get sine x? Well, if we differentiate cos x, we get minus sine x. So we need to differentiate minus cos x to get sine x. So this is actually minus 4 cos x. And always, since we're dealing with an indefinite integral here, we have to remember our plus c. Okay? Technically speaking, I should point out that we actually pick up plus c from all of these integrals. So this is actually x cubed plus c minus x squared plus c plus 4 cos x plus c for 3 different values of c, but we can actually just combine them all into one, because a constant plus a constant plus a constant is still just some other constant. Okay? And the other example I wanted to go through here was, if f of x is the absolute value function, that is to say it's equal to x if x is positive, and it's equal to negative x if x is negative, and this is the sketch of the graph of f of x equals to mod x. What's the integral of minus 1 to 1 of mod x dx? Okay, we don't have any rules for this, and I know we could probably solve it geometrically because these look like triangles and it would be easy to find the area of them, but how can we solve this kind of using the methods we've just described? Well, the important thing to notice here is this is equal to the integral of -1 to 0 of mod x dx plus the integral from 0 to 1 of mod x dx. This is by the fourth rule here. We've got a is -1, b is 1, and we're taking c equals 0. Now, why is it nice to split it up like that? It's because we can regard these bounds of integration as sets. So we're integrating from -1 to 0. That's over this region here. And when we're on this region, put 0 there. When we're on this region, absolute value of x is equal to -x, because our x is always negative. So this is actually equal to the integral from -1 to 0 of -x dx. And this one, the same argument gives that mod x is actually equal to just x when we're on the interval 0 to 1. So it's plus the integral from 0 to 1 of x dx. Okay? And now we can just naively evaluate this, and we'll get, this is -x squared over 2 evaluated at -1 and 0, plus x squared over 2 evaluated between 0 and 1. And it's pretty easy to say this first one will be -0 squared over 2 plus 1 over 2. It becomes a minus sign because when we sub in the lower bound, we have to do minus. And minus times minus gives a plus. And this one will give us plus a half. These are technically 1 squareds, obviously, but we don't actually care about that. And the overall answer is 1. Because we have, sorry, I should be clear that these ones are the things being squared, not the entire half. Okay, so that's the integral. The area underneath this graph is indeed 1, as it kind of looks like. Okay, and lastly, I'm just going to mention these for completion's sake, but these will get their own videos. And that's integration by substitution, which says that f of g of x times g prime of x dx is equal to f of u du. And the same result holds for definite integrals, except we have to be careful with our upper bounds here, that the b, the upper bound here, gets turned to g of b, where g is the function here, and a gets sent to g of a, where again g is this function here. And also, we probably want to note this for this example over here, that at the end, once we solve this integral here, we'll get an expression in u, so we need to understand that u is actually equal to g of x. That's the substitution we're making. We're saying, instead of writing down g of x all the time, we're going to write u instead of g of x. But there's a special rule that if we want to change this dx into a du, we have to say du is equal to g prime of x dx. Okay, this is quite complicated, so if you're not following this, there'll be a video about this that you can watch where we'll go into this in more detail, but I'll pass on from it for now. Just to mention the last rule, which is integration by parts, that says the integral of f of x times g prime of x dx is just equal to the product f of x g of x minus the integral of f prime of x times g of x dx. So we've moved the derivative from the g to the f, basically, because this term here should be easy to work out. Okay, and the same rule applies for definite integrals, except you just have to be careful with your bounds. You have to evaluate this function. You have to, and this notation means we're evaluating it at b and subtracting it off the evaluation at a. And we also need to evaluate the integral on the right-hand side here at a and b as well. Okay? Like I say, these are tricky things, and if you haven't seen them before, I don't expect these to make sense to you immediately, or how to use them or things like that. But we'll have videos going over them in the series coming up. Okay? But these were just the simple introduction, quick list of rules we want to work with in integration, and we'll go into further depths on them in the next videos. Okay? This has been Connor Mead, and I'll see you guys next time.